Here's the really big fun example at the end of your paper. We're going to answer 5 questions, given that this is the graph of f prime of x. For what value of x does f have a relative maximum, and why? We know f has a relative maximum anytime f prime changes from positive to negative. So I'll give my answer. So there's our answer to the first 2 questions. F has a relative maximum at x equals negative 2, because at x equals negative 2, f prime changes from positive to negative. That's the first derivative. Question 2 is, when does x have a relative minimum? F of x is going to have a relative minimum anytime f prime changes from negative to positive. So we can see that happens at 4. So just to mention, notice here at x equals 1, we do have a critical point because f prime is clearly equal to 0. But down here, f prime was negative, and afterward it's still negative. It hasn't changed sign, so we have no relative extreme value at x equals 1. That's that third piece of the first derivative test. Now we'll answer question 3. On what intervals is the graph of f concave up? Well, we know f is concave up when f double prime is positive. Problem though, we don't have a picture of f double prime. But we can actually apply the first derivative test to the first derivative. I know f double prime is positive anywhere that f prime is increasing. And I know that f double prime will be negative anywhere that f prime is decreasing. So where is f prime increasing? Any place that's going uphill. So if f prime goes uphill from negative 1 to 1, and I take the derivative of f prime, I'm going to get f double prime, and I know f double prime has to be positive. So this is my answer for number 3. So now I've written out my answer. F is concave up on negative 1 to 1 and 3 to 5 because f is increasing on those intervals. All right, so question 4, this should be easy for us. On what intervals is f increasing? Why? So we know that was from 4-1. A function f is increasing anywhere f prime is positive. So there's the graph of f prime. It's positive. It sits above the x-axis here and here. So I'll write up that answer. So there's my answer, f, that should be lowercase f, is increasing on negative 3 to negative 2, union 4 to 5, because f prime is positive on those intervals. So f prime is greater than 0. I just want to point out here, common error by D is to think that since you've seen this notation, that I'm giving you ordered pairs. These are not ordered pairs. These are intervals of the graph that just happen to have open endpoints. So do not think that you need to give a y value when you're giving an interval on which a function f is increasing or decreasing or concave up. So these are intervals, not ordered pairs. All right, and now check out question 5. At what value or values of x does f have a point of inflection and why? So when does a function f have a point of inflection? It's when f double prime changes sign. So that's where the function f, it's where the function f prime was positive and becomes negative, or was negative and becomes positive. So think back to our answer for question number 3. We knew that f double prime was going to be positive anywhere that f was increasing. Well, f is going to be concave down anywhere f prime is decreasing. So it's these places where the function f prime changes from decreasing to increasing, or increasing to decreasing, where we're going to have a point of inflection. I'll write it up. So there's your final answer. F has a point of inflection at x equals negative 1 and 3, and also at x equals 1.